Hi, Mitch Winger back with another video on data analytics and machine learning. In this video, we'll discuss supervised segmentation. Hope you enjoy. Okay, let's get started. In data mining, we look for patterns in the data that we can use. One way we can extract these patterns is to segment the population into subgroups by attribute, where each subgroup has a different value or a different average value for the target variable than the other subgroups do. Members of the same subgroup, by contrast, have similar target values. Of course, we have to use attributes which will be known at the decision time, even though we won't know the target value. This segmentation allows us not only to start generating a predictive model for our target variable, but the approach also lends itself to developing a very understandable set of rules for defining the segmentation process. So, for example, we end up saying something like, young professionals who live in Seattle are going to have a churn rate of about 14%. So, young, professional, and Seattle would be attribute values that we use to define the segment, while that churn rate, 14% in this case, describes our predicted target value. So how do we determine whether an attribute is important vis-a-vis the target variable? And this is the basic concept we use in supervised segmentation. How much does the attribute tell us? Can we automate the selection of the best attributes and then rank them, maybe? And as you might guess, the answer is yes. Let's look at one useful way we can select those attributes and how we can continue the process to create a full supervised segmentation model. The approach we'll investigate is quite useful, but it's important to remember that this is just one of several approaches to identifying useful attributes. Nevertheless, it's a good, solid approach that you'll want to keep in your bag of tricks, and something you can think about conceptually as you approach a new data science problem. So once you run into your next huge data set with dozens or maybe even hundreds of attributes, it'll be useful to think back on this idea of identifying informative attributes in order to help get started. So let's say we do have a large data set. How do we start figuring out which attribute gives us the best, the most informative partition? And in this example, we can start with a binary classification problem. Yes or no? So in the example you see on your screen, we have 12 objects. Each object may have one of two colors, orange or blue, one of two shapes, square, circle, and one of two borders, green or pink. So each object is labeled with a Y or an N, which represents the value of our target variable. So you can imagine this as the label for indicating churn, or for indicating fraud, or for indicating a potential loan write-off, or whatever. Now we can describe the feature vector for each object as the set of values for those attributes: color, shape, and border. And of course, in this practice data set, we also have the target value available. So our first question becomes, okay, we have three attributes. Which of those three attributes best segments these objects into groups that differentiate Y and N values? In other words, which attribute will give us the purest segments possible? Now, in data science, pure means homogeneous target values within that group. The closer the segment is to all members having the same target value, well, then the purer the segment. Obviously, if even one member has a different target value, then that segment is impure. Real-life data rarely has a single variable that creates pure segments. Instead, we look for ways to minimize impurities within each segment. This gives us a couple benefits. First, we have an opportunity to learn more about our data set and hopefully the greater population. You've had a chance to do this, hopefully, with some exploratory data analysis. This goes hand in hand with that process. We can also use the attributes in a predictive model. Here, we're going to try and predict the yes/no value of our label attribute. We can then make an offer, give better terms, investigate the transaction further, and so on. When it comes to selecting which attributes to use, we have a number of considerations. As we mentioned just a minute ago, an attribute rarely splits the group perfectly. Even if one of the groups ends up being pure, the other or others might not be. So consider our example that we just looked at with the objects. Let's say we eliminate that first circle. We'll imagine the data set doesn't include that first circle. So we could then use the color orange to create a pure group with value n. Of course, we only have one member in that group now, right? The blue group, of course, would still be impure. So perfect splits are rare. Next, if we do split into two groups, one with an n of 1, and then the other group has an n of 10, well, is that a good thing? Maybe a different type of split that produces a more evenly distributed pair of groups, even if each group isn't totally pure, might be better as long as we still have significantly improved the purity of each group. And of course, some attributes, categorical attributes, are going to have more than 2 values. So if we have different attributes that each have a different number of values, how do we compare the results of those splits? How can I compare a split into 2 groups for one attribute versus a split into 5 groups with another attribute? And then finally, continuous attributes. Well, what about those numeric attributes, whether they be a continuous real number or an integer? Do we create a category for every numeric value? Well, short answer is no. Luckily, we can address all of these issues for classification problems mathematically. And the mathematical formula is based on the concept of entropy and its cousin, information gain. These concepts came around in the 1940s. Let's attack them in reverse order. In information theory, entropy is considered a measure of how much disorder exists in the data set. In supervised segmentation, we can consider the whole group, but if we break it into segments, we can also consider each segment separately with respect to how pure, i.e. low entropy, or impure, high entropy, that data set or segment is. So we calculate entropy like this. We represent entropy with this h, so h of x for our data set, equals the negative sum of each target value I for every possible value I of the target. The probability of that value times the log of that probability for the value. And we can use natural log or base 2. We generally use base 2 in data science. That works out pretty well for us. So the graph to the right might give you a better feel intuitively for how it works. So we start over there on the left, and you can see all of the data points have negatives. So if we're looking for data signs with a plus sign, well, we aren't going to find any there. There's no uncertainty. They're all minuses. So we have 0 probability of finding a plus sign. We have 0 disorder, therefore 0 entropy. All values are the same. We know what the value is going to be. Now, as we move up that curve, we start to switch out some of the values, and we can see we have a mix of minuses and pluses moving up the curve until we reach the top of the curve, in which case we have an even split of pluses and minuses. So we have a 50-50 chance of selecting a plus. That's the most uncertainty we can have in this data set. Therefore, we have the most entropy, and that entropy value for that most uncertainty is 1. Now, as the distribution continues to add more pluses, you can see that we start to become more and more certain of our prediction again, because the probability for pluses is getting higher and higher. Finally, in the lower right group, we have all pluses, at which point we have a 100% chance of selecting a plus, no uncertainty, therefore no entropy. The value is 0. All right? We can calculate that using this formula, and it works like this. If we go back to our shapes that we were looking at before, we've got some no's, we've got some yeses. Those are our two possible target values I, if you will. So the probability for no is 5 over 12, 41.67%. Probability for Y is 7 over 12, 58.33%. So then we just plug those into the formula, and we only have two values, so we're going to have to do two calculations for those two possible values. Probability of no times the log 2 probability of no, and then the probability of yes times the log 2 probability of Y. We'll add those two results together. So we end up with 0.4167, and then you can use the log function on your calculator, you can use the log function in Excel, or whatever to calculate that log value, and we end up with negative 1.2630. And then for 0.5833, we end up with a negative 0.7776. And so we can add those two together. The product of those two, we end up with minus 0.4356, minus 0.5263. We flip the sign on that result. We end up with an entropy of 0.9799. We're not quite at 6 and 6, which would give us an entropy of 1, but we're pretty close, so our entropy is pretty high there. All right, so that's entropy. Now, what about information gain? How can we determine which split is the best? So let's look at this formula. Information gain for a training data set, basically the full training data set T with all of the labels marked for us. We already know what the target value is. And then we're going to evaluate one of the attributes A and partition on that. And then we'll do this for the next day and for the next day and for the next day, however many attributes we happen to have. So the information gain for the data set by partitioning on attribute A, well, basically we're going to calculate the entropy for the whole data set unsplit. They're on the left side of the right side of the equation. And then we're going to add up the entropy values for all of the possible values of the attribute based on the probability of that value in the split. So that's basically it. It's a weighted value of entropies post-split. So how do we do that? Well, let's take a look at our example. We can split our data set three different ways. We can split it on the color of the object. Is it blue or orange? We can split on the shape of the object. Is it square or is it round? We can split on the color of the border. Is that border green or is it pink? And then we calculate for each of those subgroups the entropy. And we just work our way through it mechanically. So if we split on object color, you can see we end up with two groups. The small group has 2, but we have a 50-50 split. So we have a probability of 0.5, 0.5. The larger group has 10 items in it, 6 yeses, 4 nos. So we have a 60-40 split. Next, we've got a split on shape. So the round group, we end up with 3, 2 of them with yeses. So we have a 67-33 split. On the square, we have 9. So we have 5 and 4, 56-44. And then finally down at the bottom, we have a split on border color, and we have 5 yeses and 1 no for the pink border. So that's 83-17. And then we have 4 no's and 2 y's for the green border, 33-67 for the yeses. All right, so intuitively, we can look at this and say, well, it looks like border color gave us the best split because we now have groups that are more pure than the original group. And the calculation will bear this out. So we're looking for which of these combinations of groups is going to give us the best improvement in weighted entropy. So now we do our calculations. We're going to multiply our probability times the log of that probability for the group. So in the top, we have 2 out of 12, so 0.1667. And we have 10 out of 12, 0.8333 times the entropies of those various groups, and we end up with 0.9758. Next, we have 3, 25%, versus 9, 75%, times the entropies for those two smaller groups, and we end up with 0.9729. Finally, we look at the border color. We have a 0.5 probability of getting in either one of those groups. So we multiply that 0.5 times the entropy for each one, and we end up with 0.7880. So keep in mind, our original entropy was 0.9799. And now we just subtract that newly calculated entropy for each attribute split from the entropy score of the unsplit group. Voila! Information gain. So in this example, we can eyeball the subsets like we just did to see if things make sense. Keep in mind that our original group had a 7-5 yes-no ratio, so we had about a 58% chance of randomly picking Y. In the split on object color, our chance of selecting Y are 50% for orange, 60% for the blue objects, both pretty close to our ratio for the entire group. And as you can see, our information gain is pretty small. If we split on shape, we get that similar outcome. We have 67% likelihood of choosing correctly for the circles, 56% for squares. Again, both pretty close to the full group ratio. So we get another small information gain. And as we've already discussed, our split by border color gives us 83% for pink borders, a much higher likelihood, a much higher percentage than we had for the full group, and 33% for the green border, a much lower value than we had for the original group. So both of these give us a more definitive split for each group. That is, we have a better likelihood of guessing correctly. So accordingly, the information gain is much greater, and that's the one we would choose first, border color. Now, as a plus, the notion and calculation of information gain addresses a lot of those concerns we just raised about segmenting the data. We can determine the information gain even if the resulting partitions are still impure, so we can still make that calculation. We can also calculate the information gain no matter how many categories we have. That entropy formula can be calculated for however many values of your attribute value you have, and you can split and calculate the new entropy and the weighting of that entropy for any number of values of your attribute. It also considers the number of instances that end up in each subset and weights each subset accordingly. So that just leaves the numeric attributes we have talked about as well. Well, we can do what we call binning the numeric attributes by dividing the attribute into a discrete number of value ranges. And you see this often with incomes. So you may have income groups 0 to 15,000, 15 to 30,000, 30 to 50,000, etc. Once we've done that, then we have ourselves a categorical attribute that we can move forward with. So we've completed the process of identifying the attribute with the most information gain. Now, this process can be performed independently for each of the subgroups with our remaining attributes. Of course, attributes with more than 2 values do add a bit of complexity, but the basic approach holds. So note that once we've split on border color, we can now split each subgroup using the most informative attribute for that subgroup. In this case, our next split for the pink borders, well, it could be on shape or on color, as each of those would give us 2 completely pure groups. On the green side, though, the splits would be different, and we would split on shape next, as it would also give us 2 pure groups, where if we split purely on color of the shape, we would not end up with 2 pure groups. So you can see we might end up actually splitting on different things and result with a tree that has different attributes at the same level on different branches. So calculating entropy and information gain is not particularly difficult, but even so, our data mining tools do help automate the process for us. It's still vitally important to understand how the process works, because you may be asked to explain a model, or in particular, one of the decisions it made at some point in your career. Fortunately, if you can visualize the approach we just presented for identifying informative attributes, you're off to a good start. That's it for this presentation. I hope you found it informative. As always, be sure to check out the other videos in this series.